All right, so let's start today's lecture, which is about quantization of gauge fields. So we'll finally start with the most interesting part, which is the gauge fields. As we saw from the previous lecture, the main issue with gauge fields is that we have gauge invariance, which means a redundancy in the description of the system. I mean, you can think of this in some sense as having one degree of freedom, the one corresponding to this arbitrary gauge parameter lambda, as being non-physical, as being something that can be put to whatever we want. And in order to do that, in order to deal with that, in principle, we would have to, I mean, one possibility is to choose a gauge. And this gauge acts as a constraint. And then last time we dealt with the general theory of how to do quantization in the presence of constraints. However, today we will not apply that formalism precisely, although one could. I will instead show other formalisms that are more common. Now, what kind of gauge can one choose? So one possibility is to choose something that we would call a physical gauge, in which only physical degrees of freedom propagate. And that would be, say, looking at this transformation, it would seem like we could put one of the components of the gauge field to 0. So one possibility is what is known as the Coulomb gauge, A0 equal to 0. So this, let's say, specifically puts one of the components in this transformation to 0. But of course, if we do that, the disadvantage is that we lose Lorentz invariance. This explicitly breaks Lorentz invariance because mu is a vector under Lorentz transformations. And here we put one of its components to 0. So after a Lorentz transformation, this is not the same anymore. So an alternative would be to consider a covariant, by which I mean Lorentz covariant gauge condition. The standard one being this one, which is also called Lorentz gauge. It's actually important to note this is a T, there's no T here. These are two different people, even though it doesn't seem like it. Lorentz with T and Lorentz without T are two different people. This one had the more general form, as this is responsible for the gauge. All right, so in the covariant gauge, we'll say we have covariant quantization. And of course, this is preferred because if we don't have Lorentz invariance explicitly in the quantization procedure, that means that we would have to check it at every step to be sure that we didn't do a mistake. And moreover, our results, the results of our quantum calculation will not be Lorentz invariant. So, yeah, we will have a problem. It will be awkward to calculate. All right. Let's consider this idea of a physical gauge then. Let's consider it first and see how we would go about it. So as I said, the idea would be to consider the Coulomb gauge, K0 equal to 0, but more precisely, we will see, in fact, we need to consider what is called the radiation gauge. We start with the action for electromagnetism. Which can be written explicitly, now remembering that F nu is d mu a nu minus d nu a nu. So there are two terms in here, and then when I square it I get four terms, but they are 2 by 2 the same. So then I get a factor of 2, getting minus 1/2 in front. And here two terms, the ones where I get d mu a nu squared. Now perhaps let me write it explicitly. And then the mixed terms. D mu a nu times d mu a nu. Right? And so when calculating the equation of motion, we get from this, from partially integrating this term, we'll get a box a mu. Partially integrating d mu, we get d mu, which is box. But then we get a second term from this one, right? So I vary with respect to a mu. So in here I will get then d mu, a mu. But I can also, commute the order of derivatives and write d mu in front, and here d mu, a mu. Right? And as we see, this is somewhat difficult to solve. Now, a simplification occurs if we choose this Lorentz gauge. If we choose this d mu n equal to 0, then in this gauge we get just Klein-Gordon. We just get the Klein-Gordon equation, right? And this we know how to solve. This we know it's basically just taking a Fourier transform, and then the Fourier transform equation of motion amounts to just k squared equals 0. So the solutions of this are e to the plus minus ikx with k squared equal to 0. Right? But, however, we have to remember that these are gauge fields, so they have an index, right? And then that means that if I consider a solution for a mu, I have to consider also some vector that will be called a polarization vector. And this vector has to depend on k. Because, so we're writing here the solution in momentum space, in Fourier space. But then we have this Lorentz condition acting on it, or equivalently, before the Lorentz condition, we have this extra term. And the derivatives become momenta, so there is a momentum constraint on this epsilon. So in k space, the momentum constraint becomes just k mu epsilon mu of k equal to 0, right? Derivative becomes ik mu, and then a mu is some complex number times epsilon. Okay, so this is our solution in this Lorentz gauge, is e to the plus minus ikx epsilon mu of k, where k squared is 0 and k mu epsilon mu of k is 0. But, so by the way, these things I hope that you had already when talk about electromagnetism, but nevertheless, it's very important to review them. So one observation then is that this does not completely fix the gauge. So the Lorentz gauge doesn't completely fix the gauge. And what does that mean? That means that there's a residual gauge invariance. Gauge invariance by definition means delta A mu equal to d mu lambda. And residual means that the gauge is not changed. So that means to say, if I still want to be kept to be within d mu n equal to 0, that means that I want to consider that d mu times the variation in this residual gauge is still equal to 0. And the variation would be d mu lambda. So you see, if I take this gauge transformation with d mu, that is box lambda equal to 0, then I still am within the Lorentz gauge. So I have I have this residual gauge transformation, and the interesting thing is that I can use this residual gauge transformation. So use the residual gauge transformation to fix the same one that I said before, A0 equal to 0. Let's see why that is so. So if I put A0 equal to 0, so I note that in the Lorentz gauge I have the Klein-Gordon equation. So for the field I have box A0 equal to 0, right? But then that means I can choose this gauge transformation. So I can, if I consider the gauge transformation, variation of A0 is d0 lambda, right? It's part of this, right? So I start from 0 and I get to A0. That means, so this is A0, right? Then I get that d0 box lambda is equal to 0. So I can find a lambda such that box lambda is equal to 0. And then if I find this, then I'm in this case where I keep the Lorentz covariant gauge, and yet I do this variation such that I go from an A0 to 0, right? So that means that while keeping in the Lorentz gauge, I can put A0 to 0 by this lambda. Perhaps let me call it lambda residual everywhere to make sure that it's clear that this is an extra transformation while I'm in the Lorentz gauge. All right, so the gauge the gauge choice together is this one. Now, of course, if A0 is 0, I can also say this is just the spatial part. Okay? So another way of characterizing it is A0 is 0 and divergence A is equal to 0. And this is known as the radiation gauge. Now, why radiation gauge? Well, here I assume I only had electromagnetism, but in principle I could have added a source for electromagnetism, right? And then when I vary with respect to the gauge field, I would get here J mu, well, minus J mu or something. And this would still be true. Sorry, this would still be true in the Lorentz gauge. So in the Lorentz gauge, I would have really that A mu. So if there would be a J mu, I find that A mu is, well, quote unquote, but this one, box minus 1 would mean some sort of Green's function, right? But the point is, the Green's function is act on J mu, right? And J0 in this case is charge density, right? So that's certainly something that always is there, right? The Ji perhaps cannot be, perhaps that does not exist because charges are at rest, but rho, they're certainly there. So, so in that case, you see I cannot put A0 equal to 0 because if I put A0 equal to 0, I get a contradiction, this being also equal to this thing, which is clearly non-zero, right? So, so if I have a J mu, I cannot put A0 equal to 0. So I can only put A0 equal to 0 if there is no source, in which case I have only radiation. Okay, so that's the name, the radiation gauge. I can only do it if I have only radiation. All right, so so this is the radiation gauge, A0 equal to 0 and divergence of A is equal to 0. And this is a physical gauge. So note, this is still in Lorentz. This is still implies Lorentz, so I can use the same thing that I use in here. So the solutions in Fourier space are still given by these things, right? But then you see I have an epsilon mu, and then I say that epsilon 0 of k is 0 from this condition. And from this condition in momentum space, I have k epsilon k epsilon okay, is equal to 0, right? So that means that I remove from A mu, I remove the temporal component, and I remove a parallel component. I keep only the transverse components. Temporal component and parallel component. I remove two components out of the four, and I'm left with only the two transverse, that is physical components, are left. Right? All right, so then the classical solution would be A0, A0, and then I only need to write the A vector in momentum space with the standard normalization. And then I have these two transverse polarizations, right? And here I write epsilon vector lambda of k, and then e to the I kx with a coefficient a lambda of k, and e minus I kx with coefficient a lambda dagger of k. Right? Classical solution. And then in here I have, as before, k squared equals 0 and k epsilon k is equal to 0. Epsilon lambda of k. Lambda is not an index, it's it's a counting. All right. And of course, this is a classical solution, but was chosen in such a way, including the normalization, such that these things will become A and A dagger become A dagger in quantum mechanics. Right? And to do so, I will still need to have these polarization vectors be orthonormal. That is to say, epsilon lambda of k, epsilon lambda prime of k is equal to delta lambda lambda prime. Right? All right. So how do we quantize this physical gauge? All right. So A0 is equal to 0. And then last time we analyzed at the end the example of electromagnetism, and specifically putting the constraint A0 equal to 0. Right? And we found that we can also put not just A0 but also P0 equal to 0. Remember, we found that we could shift it, and so we had both of these things equal to 0. So we can remove from quantum mechanics, from the quantization. But then we're still left with this other condition, divergence A equal to 0. So last time we got this as a secondary constraint. sorry, last time the way we found was that actually P0 is 0, but then we could put A0 equal to 0 as well. Anyway, regardless, the point was that we could remove both of these from quantum mechanics, but then we also found the need to impose this. And so, in principle, I can impose this as an operatorial condition. Operatorial condition. I mean, that's a possibility that we can think of. Of course, in the quantization, Dirac quantization, we saw that we were actually modifying the Dirac brackets and then imposing quantization with those Dirac brackets. But perhaps it's a different, perhaps there's a different way of doing it that is actually simpler. So the correct algorithmic way is the one that we described last time, but now there's a simpler way. So first of all, we write the conjugate momenta, PR or pi I, which as we saw are F0I, which means the electric field EI. And were it not for this extra condition, we would be tempted to write just the equal time commutator of the variable and its canonically conjugate, and say that this is equal to delta. So I delta ij delta 3 of x minus x prime. Or I could write the delta function as a Fourier transform of the number 1, and then I would write it like this. So that's what I would be tempted to do, but if I do so, I would still need to have this as an operatorial condition. That was what I insisted on. So that means that di in x on this thing should be 0, right? But if I act with this here, right, I don't get 0, I get ik, and this is different from 0, right? So so this is not good then. So what do I do? Well, clearly this has to do with the fact that I have too many degrees of freedom, right? Remember, we were talking about physical gauge. We just said that there are only 2 physical degrees of freedom. So there was one removed by this condition, but another one removed by this condition, right? Yeah.
Professor, where does the I represent in the delta x?
No, I mean, okay, I just mean this, right? This is the condition, right? So I remove one condition, one degree of freedom from this condition, but another degree of freedom from this condition. So here I have too many degrees of freedom. So that means I have to do something with the index I. Here I goes from 1 to 3. That's clearly wrong. I can only have 2 degrees of freedom. So remember, this is variable commuted with canonically conjugate momentum. But here I have 3. So that's not good. And so a way to deal with it, which is in the spirit of changing Dirac brackets if you want, is to change this delta ij to some other function delta ij. So here, I mean, this was iki, and as you see, I got delta ij contracted as iki, and that was not zero, it was just kj, right? But now, if I change this delta ij, I can impose that delta ij ki is equal to 0. And since moreover I want to think of this as a modification of delta ij, then it's clear what the solution is, that delta ij must be equal to this delta ij minus ki kj over k squared. Right? If I do this, then multiplication with ki clearly gives 0, because here I get kj and here I get kj times k squared over k squared. Right? That's 0. Good. So that means that so one way of quantizing is to write that ai x and t ej x prime and t is equal to I integral d3x 2 pi squared into the I k dot x minus x prime, and here instead of delta ij I write this capital delta ij, which is this factor. And then if I want to, I can write formally this as, well, I should have written this on the other side, and then I can pull it out of the Fourier integral, remembering to replace, I mean, the fact that del I is iki, right? So then ki kj over k squared under the Fourier integral really comes from del I del j over del squared, right? So this is, the I is still there. So this is thought of as I delta ij minus del I del j del squared on delta. I mean, this is formal, of course. You don't even know what this means unless you do the Fourier transform, but just as a way of saying that really it's an action on the delta function. Yeah, and then of course the other commutators are 0 as usual. Of course, that's standard. Okay, good. Now, when we do this kind of quantization, as I said, we specifically wrote the classical solution with the correct normalization here that we know is Lorentz invariant normalization, such that, well, in the present, without this polarization vector, but this polarization vectors were also chosen to be orthonormal, so they don't introduce anything new. So this is exactly like for the scalar field. And for the scalar field, when writing the solution like this, we have proven that these functions become just the A and A dagger oscillators of the harmonic oscillator. And so really the same thing goes true in here without any change. And then we obtain the same canonical commutation relations. So A lambda with A lambda prime with A prime commuted is 2 pi cubed delta lambda lambda prime, and delta k minus k prime. And the other ones are 0. Sorry, this with dagger. A with A, 0. Is A dagger with A dagger. All right. And also, as in the previous case, once we do this, we can calculate the energy, that is to say the Hamiltonian, which is, in the case of electromagnetism, as you know, and as we reviewed last time, I think, is just E squared plus B squared over 2. And also, like in the case of the scalar field, we get just A dagger plus A dagger A over 2, right? So 1/2. But now, and then integral over K. But now the only new thing is that I have this sum of the two polarizations, lambda is 1 and 2. And here, energy amounts to the energy of associated with an oscillator is K0. Right? Ki is the momentum, K0 is the energy. This is the K0. And then A lambda dagger of K, A lambda of K, plus A lambda of K, A dagger lambda of K. Yep. Okay. And also, as before, you see that, so here, this ordering is taking care now of the order. So substituting in these formulas, but being careful not to commute arbitrarily A and A dagger. So then we get this, but then this is also, of course, A dagger A, so perhaps with a 1/2. Let's say this is A dagger A plus 1/2, right? And as before, then we can see that there's a 0-point energy given by this, the sums of these 1/2 modes, and we eliminate that by considering the normal order Hamiltonian, which is this without the normal, without the constant. So yeah, sum of a lambda integral d3k to pi cubed k0 A dagger lambda of K, A lambda of K. Okay. Okay. So this was covariant. This was a physical gauge quantization. And as I emphasized at the beginning, this is a perfectly good quantization procedure, but it's somewhat cumbersome in the sense that we break Lorentz invariance, and then we have to check it at every stage to make sure that we haven't lost anything in the process. So while it is good, it is better to use a formula that is already Lorentz covariant. So there's nothing wrong with this procedure, it's just cumbersome, that's all. So the Lorentz covariant form is given in this Lorentz gauge. So the physical gauge quantization, the Lorentz gauge was implicit, but we also added this because we saw that we needed to add in order to have just physical modes. But the point about this is we want to keep at every stage Lorentz invariance. So that means that we will impose only d mu a mu equals 0, because this is Lorentz invariance. And of course, this does not fix the gauge, as we saw. We can still impose a 0 equal to 0, but that would break Lorentz invariance, so we don't do that yet. We'll see how we'll deal with that. So for the moment, we just impose d mu a mu equal to 0, and then we saw that the solution is just the solution to Klein-Gordon. So the solution and now I have 4 possible polarizations in principle, because we're still keeping Lorentz invariance, right? Then e to the I kx a lambda of k plus e to the minus I kx a dagger lambda of k. And then k squared equals 0. However, this is only a solution if d mu a mu equal to 0. However, we want to impose this in an operatorial way, as we said. So given that k squared equal to 0, that means that k mu is equal to, in some system, is equal to k00 k in some system. Right? In some system moves along the third direction. And then let's define these polarization vectors. We would still want them to be orthonormal. So let's define them to be, since we're talking about things with 4 components, and they want them to be orthonormal, just define them in the usual way. Right? So lambda is 0, 1, 2. So if we do that, then we say what? Well, remembering this physical gauge analysis, so the physical or transverse components satisfy what? Satisfy, well, the gauge condition. So this is for lambda is equal to 1 and 2. Right? So lambda equal to 1 and 2. Explicitly we see, we'll multiply this with this. For lambda equal to 1 and 2, we obtain 0, right? And that's to be expected. But we also have this unphysical components, which are the temporal and the parallel. So temporal means lambda equal to 0, and parallel means lambda equal to 3 components. And for those, we obtain that k mu epsilon mu of k lambda, right? For these ones, we obtain that this is equal to the energy of K, if you want. Right? These both give K. All right. So we see the distinction that the physical polarizations obey the Lorentz gauge in momentum space, and the unphysical ones don't. Well, but if we are to sum over all of these four polarizations, that means that the sum over the unphysical ones should cancel out. Should cancel out of quantum mechanical calculations, right? And we should be left with sum over physical ones. Okay. All right. So how do we get that? Well, remember we still have to impose d mu a mu equal to 0 as some sort of operatorial condition. So the first guess that we would have is to impose this on physical states. Right? That sounds right at first sight, because for physical states, this is the condition, which is the Fourier transform version of this. And this is what Fermi tried first. But this is wrong. And the reason for that is that if you look at the expansion for a mu, so if we want to impose d mu on this, we would get something like k mu in here, as we said, but then also minus k mu in here. But then we would have A's and A daggers, right? And the point is, this would imply, so the A part, that would be fine, because, so if we impose then d mu, A mu on the vacuum in particular, so if we impose on some physical state, it's fine, but if you would impose, it could be fine, but if you would impose this on a vacuum, for instance, from this would be obtain an A piece and an A dagger piece. And, well, while this being 0 on the vacuum would be okay, this on the vacuum would be different from 0. So we would get a contradiction. I mean, that's roughly speaking. There are some details, and one can see explicitly what goes wrong if we try to do this, but that's roughly speaking what's the problem. That we have both an A and A dagger piece, and when we act on vacuum, only the A piece naturally vanishes, whereas the A dagger doesn't. And so when we try to generalize these to physical states, so instead of 0 putting some psi, then the natural extension is to consider only the A piece, not the A dagger piece. And so the condition that one must actually take is written like this, and the notation is somewhat confusing, especially given my handwriting. The notes is obvious, but this is a plus, and it refers to the positive frequency part, which means A's, not A daggers. Okay, so plus doesn't mean dagger, it means positive frequency, which means without dagger. Anyway, and this quantization involved in this condition is called Guttav-Euler quantization, after the people who invented it. And now this formalism is Lorentz invariant, or covariant, I should say. Right? So we've written a Lorentz covariant expansion in terms of A's and A daggers, and also a Lorentz covariant condition. All right, and then we would write. So we would have to impose this condition, but the commutators in covariant quantization would be the standard ones. Sorry, you know 2 pi cubed delta. No, yeah. 2 pi cubed delta of x and x prime. No, sorry, not 2 pi cubed. 2 pi cubed comes when I write in the momentum space. That is to say, for A and A dagger. And then the other ones, mu, time, 0, and here A dagger is equal to 0. Okay. All right. But there's a problem in here. So the problem well, there's a problem either in this or in this form, of course. So the second form is obtained by expanding in terms of the creation and annihilation operators, so doing the Fourier transform and so on, right? As for the scalar field, it's exactly the same calculation. But in the first form, the problem is pi 0. As we remember, pi 0 is f00, which is 0, so that was a constraint. So pi 0 would seem to be 0, but this would seem to contradict with the commutation relation. So how do we solve that? And it turns out that the solution to this is really changing this. So if you want to impose still that A nu pi nu is I mu nu, well, then clearly you cannot have pi 0 equal to 0, right? Because if pi 0 equal to 0, you get a contradiction. So the only solution that comes to mind is to change the Lagrangian so that you change the form of pi 0 not to be 0. So we will see this next in some sense. Okay. But we also see this as a problem for the second form in terms of A and A daggers. So A lambda with A dagger lambda prime is given by G lambda lambda prime. So I think of the index lambda now as really a Lorentz index because of this. But the point is that for lambda is equal to 1, 2, 3, I get the right commutation relation. But for lambda equal to 0, I get A dagger is minus I. Sorry, not I, 1. Minus 1, right? And that's a problem because if I act with this on a vacuum, so A dagger, remember, creates the state, I would write this as this, right? So this part is the dagger of this. So this is the norm, right? But then this is equal to, by this relation, A dagger A minus 1. And in A dagger A, 0 acting on the A acting on the vacuum gives 0, and also A dagger acting on the vacuum on the other side gives 0. So this term is 0. And here, then I get minus 1. So the norm of the state excited by lambda equal to 0 is negative. Okay. So that seems like a problem. But in fact, this helps. Remembering what we said, that what should happen is that the sums of the then physical polarizations should cancel out in quantum calculations. And remember that correct positive norm have both the physical transverse lambdas 1 and 2 and non-physical parallel component 3, right? But the point is that 3 and 0, so lambda equal to 3 and lambda equal to 0, will cancel out in quantum calculations. Okay? Due to this property that, so this one has positive norm, and this one has negative norm. Now this is of course not obvious, and that's part of why this is also somewhat cumbersome. So this is Lorentz invariant, the formula is Lorentz covariant, but you have this problem that somehow you have all these extra modes propagating out. You have both the transversal and you have both the temporal and the parallel mode also propagating, not just the transverse, but these two modes will cancel out in loops. So if I have a loop, so a loop is something really quantum. It's a loop means that the particle exists only for a short time inside the loop. And here, if I would sum of a lambda, this would be sum of a lambda is 1 to 2 plus sum of a lambda is 0 and 3 in this loop. And this is a physical, and that's okay. But this is unphysical, and so this should cancel. And one can show, you can write a theorem that these two modes should cancel in all quantum calculations. Okay. So let's see how the Gupta-Boiler condition looks on states. So remembering that k mu epsilon mu for lambda equal 1 to 2 is equal to 0, then so on states states are Fourier transform in a sense, right? Where I write the Fourier transform, and inside the Fourier transform I write polarization epsilon lambda with A's and A daggers. So then on states, the condition becomes this one. But given this, what happens is really I have k0, sorry, k mu A mu lambda equal to 0. First, let's write it like this. And then k mu epsilon mu lambda equal to 3. On psi is equal to 0. But we've seen this, that both of these things give just k, the momentum or energy of the photon, right? And sorry, yeah, I forgot. Yeah, I should have. Sorry, this is times A, right? So the condition was the positive frequency part, so that's times A. And so here I have times A0 of k, and here I have times A3 of k. So both of these are equal to k. And then I can give a common factor and forget about it. And I'm left with just A0 of k plus A3 of k acting on psi is equal to 0. Right? So to see how this works, I can consider a state psi that's a linear combination of A dagger 0 and A dagger 3. So A dagger 0, let's say, plus A dagger 3 on the vacuum. And then the condition A0 of k plus A3 of k acting on this thing acting on 0 being equal to 0 amounts to now here, so these are A's, so they when acting on the vacuum give 0, right? So if I come with A0 on A dagger 3, that commutes and goes all the way to 0 and gives 0. Similarly, A3 on A dagger 0 commutes, goes to 0. So the only non-trivial term comes from the commutator of A0 with A dagger 0. Right? So when I commute A0 past A dagger 0, I get a non-trivial commutator, but then once A0 is on the other side, it again gives 0 acting on vacuum. And the same thing from A3 with A dagger 3. Okay? So the condition. So I chosen this state because I know it's a physical state, but now we're checking it. Now we're checking that this equation is true. That the commutator of A0 with A dagger 0 plus the commutator of A3 with A dagger 3 is actually 0. And that is true because, as we saw, so the parallel component had A with A dagger 1, as it should be, but the temporal component had A with A dagger minus 1, right? So the unphysical modes cancel against each other. That's what we said. Okay, so A with A dagger cancels against 0 with 3. Okay? So what did you see here? Well, of course I could have put in here A dagger 1, A dagger 2. The physical modes, that's not a problem. The physical modes never give a problem, right? Because K mu epsilon mu K is equal to 0. So as we saw in the Gupta-Euler conditional states, I only have the 0 and 3 components of A. So having physical modes acting on the vacuum, it's fine. The question is only what happens with unphysical modes. So the unphysical modes come in this combination. They always have to come in pairs such that they cancel out in calculation. Okay? Okay. And finally, let me make one more observation. So it would seem like this is a stupid thing to do because, well, after all, if you think of A mu as the classical field, the full condition was that d mu A mu is equal to 0, not a part of d mu A mu, right? So why is this a good condition? Well, the point is, if you think about quantum mechanics, this is not the thing that should become classical. By the Ehrenfest theorem, the thing that should become the classical condition is the vacuum expectation value, not a state condition, right? So, really all we have to check is that this thing is 0. Right? If this is 0, this is what becomes classical by the Ehrenfest theorem. Right? And this is 0 because I write this as d mu A mu minus of k plus d mu A mu plus of k psi, by which I mean the minus has A dagger and the plus has A, right? A it is. But psi with A dagger, so this is A on psi dagger. So this is 0, right? So if this is 0, then this is 0. Okay? So imposing this d mu A mu plus on psi from the right is 0 implies psi from the left d mu A mu minus k is equal to 0. So that means that this is true and we get the correct classical condition. Alright? Good. So we've checked that our quantization becomes really the correct classical condition. Alright, so now let me pause and comment. So I've shown for you two ways of quantizing. One in a physical gauge and one in a Lorentz covariant way, the Gupta-Euler quantization. Okay, to come back a little bit. So in the physical gauge, I had to impose both A0 equal to 0 and divergence A equal to 0 to eliminate both unphysical components, right? Whereas in here, at first I didn't do anything, right? I just wrote a quantization condition and then I imposed a d mu and mu, I mean half of d mu and mu equal to 0 on states, right? But by doing so, I still have these propagating unphysical states, like the temporal and the parallel. Just that once I impose also d mu and mu plus equal to 0, I have to obtain that in quantum calculations, the two unphysical modes cancel against each other. Okay? So it's a good quantization from that point of view. So I keep these unphysical modes, but they will cancel in quantum calculations. But there are other ways of quantizing. So, of course, I could choose other gauges. That's certainly a possibility. Then there are more modern other gauges, in particular an important one that is also used, but I haven't given it here, is light point quantization. This is particularly important for string theory, but in gauge theory is not so used, so that's why I didn't describe it. But it's theoretically important. But then there are more modern ways of quantizing. Chief among those is what is called BRST quantization. But I need to describe BRST symmetry first. And second, this is only interesting in the non-abelian case. So, outside the non-abelian case is less interesting. It seems somewhat trivial. So because of this, this is addressed in quantum field theory too. And well, there's also generalizations of this VV and anti-field formalism. Anyway, and then there are path integral procedures. So one way to do things, so yeah, these things are a combination. Their BRST ways are also make more sense in path integrals. So, but in a path integral, the simplest thing you could do is to use a Hamiltonian approach, treating the constraints a la Dirac. So Dirac quantization in the path integral. I haven't done this, but for instance, among the books that I know, the book by Pierre Ramon does that. So if you're interested, you can see that there. But the one procedure that is by far the most common and used in well, in quantum calculations that refer to phenomenology, for instance, is Fadeev-Popov quantization. And this is one that I will be describing next. But also, this easily generalizes to the non-abelian case. All right, so before we deal with the quantization per se, I want to make an observation that we will use as I said, in this Lorentz covariant way, we need to deal with the fact that pi 0 is equal to 0, apparently. And the way to deal with it is to change the Lagrangian. And how do we change the Lagrangian? Well, it would be nice if I would obtain just Klein-Gordon from the Lagrangian, because that's what we used anyway. When expanding the gauge field A mu, we use just Klein-Gordon. So, remember, this is just a guess. So, the point was we wanted to get rid of the term in the equation of motion that contained, so there was a term that contained d mu, a mu. We wanted to get rid of this term, right? And that was from varying with respect to a mu. And so you see, and this comes from a partial integration, you see that it's natural to guess that a good term to add to the action, to the Lagrangian, would be d mu a mu squared. Because I already have this, and then this acting on this also. So, I'm guessing that this is a good Lagrangian. Now, of course, this is no longer gauge invariant, right? But that's fine. The whole point is to deal with a way to fix gauge invariance. But so it's not gauge invariant, but it's Lorentz invariant. So that's what we wanted. So the equation of motion then is logs a mu minus. So here we had this extra term, d mu a mu, right? And from here you see when I vary respect to a mu, I get a factor of 2 cancelling this. And then the partial integration changes the sign. So then I get plus lambda times this same term. And so we see that if lambda equal to 1, I just get Klein-Gordon. So lambda equal to 1 is called Feynman gauge. I put it in quotation marks because it is not a gauge. It's just a misnomer. Right? It's a choice. It's a choice of a parameter in the Lagrangian. It's not a choice of gauge. The gauge we're doing is Lorentz gauge. This hasn't changed. But what we're doing is you're choosing a parameter in the Lagrangian. And for historical reasons, this is called Feynman gauge. Well, so the way we arrived at it was just a simple way to deal with this fact. We didn't want to obtain pi 0 equal to 0, and we wanted to obtain the Klein-Gordon equation. But we will see that this is actually what we obtain. This is the Lagrangian that we actually obtain from the Popov quantization procedure. So, Now, to properly define this, we need to work in Euclidean space because, as we saw, path integrals are best understood in Euclidean space. So, we need to Vic rotate time to minus Euclidean time x4, minus I Euclidean time x4. However, this is what happens for so this is what happens for x mu. But we also have a vector a mu, and so this should follow what happens to x mu down, which is minus t, which changes to the same minus I, to minus t changes to plus I squared plus I squared. Okay, so that means that a0 should go to plus I a4. And also things like f0i should go to plus I f4i for the same reason. Then we saw that the point of the Vic rotation was that I times the Minkowski space action is Vic rotated to minus s times the Euclidean action, right? Such that I integral dt times minus fij squared over 4, the spatial components that are not Vic rotated, this became minus integral dx4 fij squared over 4, right? That was, from this part, I took from this Vic rotation of the action, I took the part that has trivial indices, spatial indices, unchanged, and this went this way. But in Euclidean space, when I Vic rotate, all indices are Euclidean, so all behave the same way, which means that the Lagrangian in Euclidean, so this is the minus from in front of the action, this was just the action. So now the full action in Euclidean is just the generalization of this. F mu Euclidean, F mu Euclidean, right? And as before, I can write this as 1/2. So I can write this as 1/2, and then here I would have this thing is b Euclidean squared. But now the f4i piece, so f4i now is ei. This is maybe like this, ei Euclidean squared. Okay? So in the Euclidean space, this is just like the Hamiltonian, Euclidean Hamiltonian, which is what's always the case. And, well, as before, the Euclidean action is integral d for x of the Euclidean Lagrangian. And one of the points about path integrals, so the first point about Euclidean space was this fact, the minus regulates the phase, so e to the I s Minkowski becomes e minus s Euclidean. So phases become exponentially decaying objects. But the second point was the fact that in Euclidean space I don't have boundary terms anymore. So Euclidean space, if you remember, meant that there is no boundary terms anymore. So I can do partial integrations without thinking about boundary terms. So the point is, the Euclidean theory was defined as actually the radius going to infinity limit of a theory with periodic time, right? Which therefore did not have boundary. It was a space without boundaries. Well, in time. So I can partially integrate this action. So I can partially integrate. And so as before, I have 1/2 times this thing. But here, d for x. All right, so maybe let's write this a little bit more in detail. So before I had minus a quarter Fij, now I have plus a quarter f mu, f mu. But this was d mu a mu minus d mu a mu. And when I partially integrate, I would get minus a mu d mu a mu from one term, and then from the cross term I'll get plus a mu d mu a mu sorry, d mu. Right, here it is. Yeah. So I get 1/2 times a mu, and here I get this term, but in order to write it the same as the second term, on the right hand side I'll put a mu, which means I write this term as minus box del squared, but then times delta mu. And then this term is just d mu, right? And then the path integral is path integral over a mu, and then of this exponent minus the Euclidean action. So minus 1/2 integral d for x minus this a mu minus d squared delta mu plus d mu a mu. Okay. And in principle, I would want to write this. Remember what we did for scalars and fermions. I would want to write this as some normalization constant z of 0, then exponent 1/2 and j of x, j of y, and here the propagator. So this is what I aim to write it as, right? But the point is, G mu nu as the propagator should be the inverse of this kinetic propagator. And the question is whether this kinetic propagator is actually invertible. If it would be invertible, then this would be a natural equality by what we already did for scalars. Right? But the question is such a propagator invertible? And the answer is no, it's not invertible. Because it has zero modes. Right? And not just any zero modes. So the point is that the zero modes are what we thought they would be. The zero modes associated with gauge invariance. So if I write this, then minus d squared delta mu plus d mu times this. So now I replace a mu by delta a mu, and then I substitute delta a mu is d mu lambda. Then this is actually 0, because you see here I get del squared, right? Sorry, not here, whatever, nu, right? Here I get del squared times d mu, and here also I get d squared times d mu, right? Right? All right, so we have a problem, and we were expecting this problem. We have these unphysical gauge transformations, which now appear as zero modes of the kinetic operator. So we have to eliminate them. So we have to eliminate the zero modes of the kinetic operator, which is the analog of gauge fixing, right? Gauge fixing eliminates these zero modes from the theory, but now we have to do it in some other way, not just gauge fixing. And the way invented by Fadeev and Popov is to notice that we're dealing with path integrals. And moreover, I wrote here z of j, but remember that in physical quantities, what we find is ratios. So in physical calculations, we find ratios of z's in which vacuum bubbles cancel. Right? So we have z of j over z of 0, things like that. Right? We've seen that vacuum bubbles cancel between the denominator and numerator by a process of factorization. So these unwanted infinities in the vacuum bubbles factorize in the path integral, and they cancel in the numerator and denominator. So perhaps it's enough for the same thing to happen to gauge invariance. So it's enough if the integration of the gauge invariance factorizes. Okay. So this volume of the gauge invariance or product over all possible x's of d lambda of x. Or another way of saying it is the volume of the symmetry group. So that's also a possibility. That the symmetry group is U1, right? But U1 at each point, it's local symmetry, that is local gauge invariant. So the product of all the possible x's of these U1s has to factorize somehow. All right, so let's see how to do this. So to do this, I choose a more general gauge covariant condition. So choose a more general covariant gauge condition. So my gauge condition was d mu a mu of x equal to 0. But instead of being it equal to 0, I put it equal to some scalar function c of x. Right? This is still gauge covariant, Lorentz covariant. Right? So the Euclidean Lorentz gauge is d mu a mu equal to 0, that is c of x equal to 0. All right. Now, a small technical point is we have to think of the space of all possible a's, and in it, let's consider the so-called orbit of A. That is, we start with a given A, and then we apply gauge transformations. From A, and this is a subspace in the space of all possible A's, right? Then if I vary this initial point, the sum of all the orbits will give me the whole space. But and then also think of the space of all possible gauge conditions. Sorry, M of A, let's call it. Well, not even of A, let's call it like this, just M. So these are things like this, right? This is a gauge condition. Okay? And the question is whether there's a unique intersection point. So first of all, it has to exist, and second, the question is whether it's unique. That is, I start with an A, and I make a transformation with a parameter lambda that depends on A, such that I go to the space of all possible gauge conditions, right? So for our purposes, it's enough to think about this existence, and we explicitly can see that, we'll explicitly see that this is possible. Also because I'm treating here Faddeev-Popov quantization of electromagnetism. The second part is irrelevant, but it's an important point to remember in general. There are what are known as Grigov copies in non-abelian gauge theories, which means that this last part, uniqueness, is not true. However, what is true is that there is a unique infinitesimal transformation. I should say not infinitesimal, connected with a unity. So there are large gauge transformations that lead us to Grigov copies. That's a rather technical point. There are people who work on these Grigov copies, and it's a difficult issue, but this is in the non-abelian case. We're not interested in here. All right, so let's say just constructively, we'll see that there is such an intersection. So, if I vary a mu with a lambda of A, right, this would be d mu lambda of A. So after this variation, I want this to be equal to the gauge condition. So that means that d mu lambda of A should be equal to minus d mu A mu plus C of X. Right? All right, and so if in Euclidean space, in the case of in electromagnetism, if C of X decays sufficiently fast at infinity, well, and the mu as well, then there's a unique solution. So, so then it makes sense to write it like this. So to write lambda as lambda of A, because that is that unique solution. Okay. And then I also call, in general, not necessarily for lambda of A, but in general, I call A mu lambda the A mu transformed by some lambda. Right? And then I have the following lemma. I think it's with a minus. Well, integral of a product of x's of this d lambda of x. So this is the factor that I said I want to factorize. This is the volume of the gauge invariant that I want to factorize. Time is integral times, product of a y delta of minus d mu A mu lambda of y plus C of y. So this thing where A mu is the transformed A mu. So this thing is equal to 1 over determinant of minus del squared. Let's prove this. mu, this thing minus d mu of a mu lambda plus c. By definition, a mu lambda is a mu plus d mu lambda, so minus d mu a mu minus del squared lambda plus c. And then I remember that I defined, given an initial a mu, I defined lambda a such that after the transformation with lambda a, I get c. So the definition was this: d mu lambda a is minus d mu a mu plus c. So I write this then as minus del squared lambda, this term, and then the remaining two terms I rewrite as this one. So plus del squared lambda a. Okay, so the thing that appears in the delta function then, thing that appears in the delta function here, is minus del squared of lambda minus lambda a at y, right? And then the only thing I do, so this is under an integral of all lambda of x's, right? But in this integral of all lambda of x's, I make the change to lambda minus lambda a. Right? I shift the integration variable by lambda a. Right? Lambda is an arbitrary one, but lambda a is not. Right? Lambda a is the difference between a and this this line. And this point was supposed to be unique, so both a and final point are unique, means lambda a is a fixed function, right? This is a fixed function, which means it's really like a constant from the point of view of integration. It's just shifting the integration by a constant, right? Because for each given x, this acts as a constant. And so the shift is trivial. Right? So this is now called lambda prime or tilde or something, and I can remove the tilde. And so this now becomes my lambda. Right? So I find that the left hand side is equal to just integral pi of x product over x d lambda of x times this delta function of minus del squared of lambda of x. Right? Oh, sorry, yeah, pi of y. Okay. But on the other hand, this is just a continuum version of, if I would write, here there would be some operator delta ij, right? Remember, the derivative is thought of as a matrix in xy space, right? This is already from quantum mechanics, you should know. So that so this is a continuum version of some operator acting on lambda j. Right? And I know what this is, right? This is just one over determinant delta. Right? I mean, from the definition of the delta function. So here delta corresponds to this operator minus the del squared of x and y, thought of this way, right? Or if you want, you can put this on the other side. That's another way of thinking about it. But anyway, so the result then is that, as we said, we get one of the determinant, which is proving my lemma, right? Okay, so now let's use this lemma in the path integral that we have. Well, to do so, I write this as 1 equal to, so I put the determinant on this side, I write integral pi over x d lambda x, determinant minus del squared, pi of y, delta minus del squared lambda, of minus d mu a mu lambda plus c, 1. All right, and I put 1. Well, I put on quotation marks. This is really 1 the way I wrote it. However, now I write something that is truly in quotation marks. I write 1 of lambda, 1 of alpha, by which I mean anything that does not depend on my variables is a constant from the point of view of ratios of partition functions, and therefore it's irrelevant. So I call it 1 of alpha, by which I understand that it's something that will not give any contribution in physical quantities. So this 1 of lambda, by this I mean path integral over c of x, e minus 1 over 2 alpha, integral c squared of x times this 1, right? Now this was actually 1, well, perhaps there was some numbers here as well, but that I didn't care. But now this is not 1 anymore. This is a function of alpha, right? This is a path integral over c of x, but it's a function of alpha. But I don't care about that. Now I substitute this 1 with this. But now now in substituting, so I write integral pi of x d lambda of x, determinant minus del squared, and then I have this e minus 1 over 2 alpha, integral d dx, and here I would write c squared x. Just that my 1, so I've written this part, but now I have this part. And this is just product over all the variables of delta of this thing. So c of the variable is equal to this thing. So I can just replace here, right? I replace c of the variable with this. So minus d mu a mu lambda squared, right, of x. All right. So now we want to use this in a path integral. So let's say I have this path integral, right? Integrals over, path integral over A, weighted with e minus s, and then I'm calculating some observable, some operator depending on a mu. But then in this thing, I insert this 1 of alpha, right? Which again, this is a bunch of numbers and functions of alpha which are irrelevant, that will cancel out when I divide by the same thing when I divide by this, right? Without the operator, the 1 of alpha will cancel. And then this is equal to this thing. So determinant minus del squared, integral phi over x d lambda of x, and then integral dA mu e minus s a mu, and then I still have this minus 1 over 2 alpha integral ddx d mu a mu of x squared. Okay, and yeah, all a mu. Sorry, a mu lambda. This is a mu lambda here. But the last step is really to change. So this is a path integral over a mu, but now the same logic as before. Lambda is a given function. Remember, you go from original fixed point A to point lambda, to a point, to the unique point that intersects, which is now a mu lambda, right? So I make the change to a mu lambda, right? Instead of a mu, integrate over a mu, I integrate over a mu lambda, because the difference, this lambda a, was a fixed function, right? That was now was a constant for the path integration. And then I just forget this lambda. So I replace this with a mu lambda, and then in here I would have a mu lambda as well, but then might as well call it a mu everywhere, right? So the final result is this, right? And note that this thing is now a common factor, right? And I'm left with a path integral where indeed I changed the Lagrangian, right? I changed the action, that is to say, from s to s plus 1 over 2 alpha integral dA squared, which is just what I used before, right? So as I said from the beginning, when I calculate something physical, like for instance the verb of this operator O, what I do is I take ratios of these things, E minus the action with O, perhaps something else, right? And then I can add for free also this 1 of alpha, because that's a constant. And then this is the ratio with the thing without the operator, right? Right? And then in both numerator and denominator I do this, I apply this formula. And that means that this thing that factorized will cancel, and here I get just this extra term in the action. Sorry, with away here and here without. Okay? So, after all this, we've seen that we have an effective Lagrangian. The effective is from dealing with the issue of gauge degrees of freedom, gauge fixing, and it amounts to just adding this term 1/2 alpha d mu a mu. And since this breaks gauge invariance, and as we saw, this was a deal to deal with a way to deal with gauge invariance. This is called a gauge fixing term. So this eliminated the zero modes of the kinetic operator. Right? And the final observation is with respect to what we said before. Alpha is 1 over lambda, right? Before I had written the same term, but as lambda over 2 dA squared. So alpha is 1 over lambda, so lambda is 1 is the same as alpha equal to 1. And this is the so-called Feynman gauge. Though I didn't, as I said, it's not really a gauge. Okay. And now we can actually invert the kinetic operator, and we can write a propagator for the photon. Right. So now this effective action, as before, is 1/2 a mu minus this del squared delta mu plus d mu d mu. This was what we had before, but now I get this extra term, and from partially integrating we get from partially integrating we get minus d mu squared, 1 over alpha minus d mu squared, acting on the same thing. So minus 1 over alpha. D mu. I had d mu a mu with d mu a mu. So when I partially integrate this, I get minus 1 over alpha times the same thing. So in other words, I just put one product of 1 minus 1 over alpha. Okay? And this thing is now the inverse propagator. And I can, of course, write this as a Fourier transform. or now this G minus 1 inverse is, so d mu becomes I k mu. So this is k squared delta mu minus k mu k mu, 1 minus 1 over alpha, right? And inverting it means writing k squared delta mu minus k mu 1 minus 1 over alpha times g mu lambda, let's say, of k equals to delta mu lambda. In other words, g mu of k, propagator, I have to put a 0 to remember that it's just a kinetic term, is, well, you can see here, this is, I can put k squared outside, and then this inverse 1 over k squared, and in here is delta mu minus a term proportional to this, and it's actually 1 minus alpha. Now we can check, yeah, maybe you want to write it with mu lambda, make it easier. So now multiplying this with this, we see we get this is delta mu. Then this thing times this thing, we get k squared over k squared, that cancels, so we still get k mu k lambda over k squared. So plus, and this is alpha minus 1 over alpha, here 1 minus alpha, k mu k lambda over k squared. Then this times this gives the same k mu k lambda over k squared, but then minus alpha minus 1 over alpha, this, and then this times this gives the same term, but now with minus 1 minus alpha. Okay, so all in all, we get alpha minus 1 over 1 minus alpha is minus 1, so minus 1 over alpha, then minus alpha minus 1 over alpha is minus 1 plus 1 over alpha, then finally minus 1 plus alpha. And it didn't work. What did I do wrong? No, so, yeah, no, it is like this. Minus 1 over alpha, plus 1, minus 1 plus 1 over alpha, minus 1 plus alpha. And minus.
Instead of 1 minus alpha, shouldn't it be alpha over alpha minus 1?
Oh. Yeah. This is alpha minus 1 over alpha. Sorry. 1 minus 1 over alpha times 1 minus alpha. I'm stupid. Yeah. So this is so this is what? Alpha squared, so minus alpha squared plus 2 alpha minus 1 over alpha. That's minus alpha plus 2 minus 1 over alpha. Okay, then minus 1 plus 1 over alpha. And then this. Yeah, and now. Now that just gives 0, no? Right, that was the point, yes. That gives 0, yes. That's indeed the point. So this can cancel and get just that terminal out. Okay. All right, so this is the propagator. And as we said, alpha is 1 and is called Feynman gauge. So in Feynman gauge, alpha is 1, so the propagator is just 1 over k squared minus delta mu. Okay, so it's just the Klein on the propagator. Okay. All right, so that's everything I want to tell you today. Do you have questions about this? No? Okay. Let me stop this here.